Leave an iron nail out in the humid air, and over time it blooms into rough orange rust. Milk left at room temperature in the summer sours and thickens. In both cases, the initial substance seems to change its very identity, appearing to become something else entirely. The transformation is even more startling when a strip of magnesium ribbon combusts. The solid metal erupts into a dazzling white flame, leaving behind nothing than a fragile pile of white ash. To our eyes, it looks as if the metal has simply burned away into nothingness. However, if we burn that magnesium inside a sealed chamber and weigh the entire system, the scale wouldn't move a fraction of a gram. While the ribbon vanishes, the total mass of the materials involved remains exactly the same before and after the flame. The solid magnesium is still there. It has simply merged with invisible oxygen from the surrounding air to form the white powder we call magnesium oxide. Tracking these invisible handshakes across a chaotic reaction requires a precision that our physical senses can't provide. To account for every single atom involved in these changes, we use the chemical equation, a symbolic shorthand that ensures the amount of matter entering a reaction matches the amount coming out. Consider the reaction between iron and steam to create iron oxide and hydrogen gas. We can represent this change as a basic word equation, listing our starting reactants on the left and the resulting products on the right. When we translate those words into chemical formulas, we get a skeletal equation. But look at the numbers. We have one iron atom entering the reaction on the left, but 3 iron atoms appearing in the product on the right. A literal reading of this equation suggests we've created 2 iron atoms out of nothing, which violates the fundamental balance of mass. To fix this, we have to audit the atoms. During this audit, the chemical formulas are locked. Water is H2O, and we cannot change its internal subscripts to the Menneth work. We can only adjust the total quantity of the molecules themselves. This forces us to use a hit-and-trial method, testing different quantities until the number of atoms on both sides of the arrow is identical. This is the only way to accurately map how the reaction actually occurs in nature. We begin by identifying the compound with the most atoms, the iron oxide on the right. Specifically, we need to address those 4 oxygen atoms. To match them on the left side, we add a numerical multiplier, a coefficient of 4, in front of the water molecule. While the oxygen is now balanced, we've created a new discrepancy. Those 4 water molecules now give us 8 hydrogen atoms on the left, while we only have 2 on the right. We fix this by adding a coefficient of 4 to the hydrogen gas on the right. Now we have 8 hydrogen atoms on both sides of the ledger. Finally, we address the iron. By adding a 3 to the iron on the left, the equation reaches perfect equilibrium. Every atom is accounted for. To complete the picture, we add the physical state symbols. Solid iron reacts with gaseous steam to produce solid iron oxide and hydrogen gas. This balanced equation proves that no matter was lost or created. The atoms simply traded partners in exact, predictable ratios. Once we can read these ledgers, we see that the universe reorganizes matter using a few consistent mechanical patterns. The first is the combination reaction. This occurs when 2 or more separate substances merge to construct a single, more complex product. This assembly is typically exothermic, meaning it releases energy. This is the process that provides the energy our bodies need to stay alive during respiration. The opposite pattern is the decomposition reaction, where a single complex substance is broken down into simpler pieces. Pulling these atoms apart requires an energy payment, whether that's in the form of heat, sunlight, or an electrical current used to split water molecules. While the physical world is in constant flux, the chemical equation provides proof that even in the most violent transformations, the total number of building blocks remains perfectly constant. If you mix the right substances together, you get violent explosions, sudden color changes, and thick plumes of gas. To the naked eye, these events appear to be unpredictable chaos, but underneath the surface turbulence, the process is governed by a rigid constraint. An atom of one element never morphs into an atom of another. Matter does not vanish from a mixture, and it does not materialize out of thin air. We can see this accounting by looking at the elements involved in the thermal decomposition of lead nitrate. When the reaction begins, the compound fractures into its component notes: lead, nitrogen, and oxygen. When we tally the atoms before and after the reaction, the count is identical. We begin with 2 lead, 4 nitrogen, and 12 oxygen atoms, and we end with that exact same inventory rearranged into 3 new substances. A chemical reaction is specifically the mechanism of breaking existing bonds and making new ones to produce these different configurations. Because atoms are conserved, we can categorize nearly all chemical behavior into 5 foundational structural pathways. Identifying these specific permutations allows us to predict how different substances will react before they ever touch. These pathways are dictated by the conservation of mass and the specific ways energy is transferred during the bond-breaking process. By focusing on this structural matrix, we can analyze chemical change as a series of predictable reorganizations rather than a collection of isolated events. The first architecture is the simplest: combination. This occurs when 2 or more distinct reactants converge to form a single, unified product. For example, when water and calcium oxide meet, they lock together to form one substance, calcium hydroxide. If you touch the beaker during this reaction, you will feel a sharp increase in temperature. This occurs because the formation of these new, stable bonds often results in a surplus of energy that the system must expel into its surroundings. We define this release of heat as an exothermic reaction. This process is the same mechanism that powers human biology. Cellular respiration is a continuous exothermic combination reaction. Inside your cells, glucose combines with oxygen to form new bonds, releasing the energy required to maintain life. In this model, combination is a shift toward a lower energy state, providing the thermal and chemical energy used in everything from industrial chemistry to metabolic function. The second architecture is the inverse of combination. Here, a single reactant fractures into simpler, separate products. Because stable bonds are being broken rather than formed, the system requires an input of energy to proceed. Reactions that must absorb energy from their environment are known as endothermic. One method of forcing this fracture is through intense heat. Applying thermal energy to limestone decomposes it into quicklime and carbon dioxide. This thermal decomposition is the central reaction in the manufacturing of cement, which provides the material basis for modern infrastructure. We can also use electricity as the energy source. Running a current through water provides the energy necessary to pull the hydrogen and oxygen atoms apart. A third source is light. When white silver chloride is exposed to sunlight, it absorbs photoenergy, which separates the silver from the chlorine gas and turns the material gray. This specific photo decomposition was the chemical basis for all black and white photography before the digital era. Whether the energy source is thermal, electrical, or light-based, the structural result is the same. These reactions demonstrate that chemical compounds will not break into simpler parts without a constant input of external energy. The third pathway involves atoms swapping partners. In single displacement, an element replaces another within a compound. When raw iron enters a copper sulfate solution, it displaces the copper. Iron takes its place next to the sulfate, leaving the copper to settle as a solid. This swap is driven by a reactivity gradient, where more reactive elements, like iron and lead, consistently displace less reactive elements, like copper. In double displacement, 2 different compounds execute a mutual trade of their ions. Barium chloride and sodium sulfate, for example, exchange their partners simultaneously. This exchange often results in a new molecular pairing that cannot be dissolved in water. When this happens, we call the result a precipitation reaction. Visually, this appears as a clear liquid that suddenly clouds and solidifies as the new, insoluble substance falls to the bottom of the container. These reactions reveal a hierarchy where atoms reorganize into more stable reactive pairings or leave the solution entirely as solid precipitates. The final typology is defined by the transfer of oxygen or hydrogen between substances. We call these redox reactions. Oxidation occurs when a substance gains oxygen. When copper is heated in air, oxygen atoms bind to form copper oxide. Reduction is the opposite. If hydrogen gas passes over that copper oxide, it loses its oxygen atoms and reverts to pure copper. This same structural logic applies to hydrogen. If a substance gains hydrogen, it is reduced, and if it loses hydrogen, it is oxidized. Crucially, these two processes are always coupled. One reactant cannot be oxidized unless another is simultaneously reduced to accept the transferred atoms. Redox reactions show that many chemical changes are a zero-sum game of elemental transfer. These 5 pathways, combination, decomposition, single displacement, double displacement, and redox, form the structural matrix of chemistry. In every quadrant, the total count of atoms remains constant. Bonds are broken and reformed, but the underlying matter is never destroyed. The force driving these shifts is the transfer of heat and the movement toward more stable chemical states. This systematic lens provides a framework for organizing chemical data, turning a list of reactions into a predictable map of atomic behavior. From the industrial production of cement to the mechanics of a cell, these 5 pathways dictate how matter reorganizes itself throughout the physical world. When a piece of iron is freshly forged, or a batch of food comes right off the line, they share a certain perfection. The metal is shiny and structurally solid, and the food has a rich, satisfying profile. But the second those items leave the factory floor and hit the open air, a clock starts ticking. They immediately begin degrading, under pressure from an invisible force. That force is oxidation. It's a relentless chemical reaction between the materials we rely on and the oxygen in our atmosphere. At a microscopic level, oxygen molecules aggressively bond with the surface, physically tearing away its structural integrity atom by atom. Because oxygen is everywhere, we are trapped in a perpetual two-front war against this chemical thief, fighting to protect both the infrastructure we build and the food we eat. On the first front, we deal with inorganic decay. When metals are attacked by surrounding substances like moisture and acids, they corrode. You see it on bridges and iron railings. Oxygen reacts with iron to form a reddish-brown powder coating, a process commonly known as rusting. On a massive cargo ship, constant exposure to moisture accelerates this breakdown, eating away at the hull's thick steel plating. It also attacks our everyday consumer goods. Left unprotected, the metal bodies of cars break down and flake away under that same chemical pressure. That reddish-brown powder is actually damaged iron. Every year, we spend an enormous amount of money replacing these weakened metals before the structures completely fail. Iron takes the brunt of the damage, but almost all metals get tarnished by oxygen. Each one just leaves a distinct visual signature. When silver corrodes, the oxidation coats the surface in a dull, heavy layer of black. If the metal is copper or bronze, the reaction creates a distinctive green coating, often called a patina. Red rust, black tarnish, or green patina. Our eyes see different colors, but the chemistry is identical, oxygen slowly claiming the metal. Now we pivot to the second, far more fragile front, our food supply. When oxidation specifically attacks the fats and oils in our food, the process is called rancidity. The chemical alteration of rancidity leaves the structure intact, but mutates the food's smell and taste. While infrastructure decay is slow and highly visible, organic decay happens fast, and we detect it primarily through our senses of smell and taste. Oxygen makes no intellectual distinction between an iron beam and a fatty snack. Its nature is simply to break down the chemical bonds of whatever it touches. We aren't helpless against this chemical countdown. We have engineered deliberate defenses to keep oxygen out. For our food, the first line of defense is chemical. We add specific substances called antioxidants to neutralize the oxidation process before it can start. Next is the mechanical approach. By keeping food in airtight containers, we build a wall that physically blocks out the atmosphere and slows the reaction. But blocking out air is a massive logistical challenge when packaging millions of units on a factory line, like these potato chips. To solve this, manufacturers flush bags with an inert gas, like nitrogen, pushing oxygen out before sealing. The bridges we drive over, the cars we drive, and the shelf-stable foods we eat all survive because we have learned to engineer barriers against the relentless, invisible power of oxygen.